Hello everybody, Mr. Hasty here. What we're going to be talking about today is a particularly tricky part of calculus, rotating regions around horizontal and vertical lines. So we've been talking about if we have a particular region in two dimensions and we want to rotate that around either our x or y axis, that we can use the washer method or the shell method. What we're going to do is we're going to extend this concept to rotating around lines that are not just the x and y axis. For instance, this could be the line y equals -2, or maybe we want to do a vertical line. Maybe we want to rotate this region around the line x equals -2. There are two ways that people generally go about this. I prefer the first method. I'll briefly discuss the second method, and I'll talk about why I prefer the first method. The first method is to adjust our geometric reasoning. So, when I say adjust our geometric reasoning, before, when we were rotating around our x-axis, we would think of this distance right here as our radius. And the equation of the curve would be the radius we would use. Now we're simply going to add 2 to that because our radius is 2 units further there. We'd also need to recognize that this is not just a circular cross-section, but there would be a washer because there would be empty space there. That's the method that I'm going to choose to do. We're going to adjust our formulas and equations as we go to adjust for those distances. The second approach is to apply transformations. So, what do I mean apply transformations? If we want to take the region as shown in the picture, we could draw an equivalent scenario . If we rotate this particular region around the x-axis, it would have the same volume as the previous example up here. The reason I tend to avoid applying transformations is twofold. Number one, a lot of the problems we do from the text and on the problem sets and things like that involve taking the same region and rotating around multiple different axes. That is a lot of work to reapply transformations each time in order to get a completely new graph in order to do the volume of that particular graph. So to avoid that extra tedious work, we're going to just work on adjusting our geometric reasoning, which is quicker if you understand it anyway. So we're going to take one region and we're going to rotate it around 3 different axes to show the method here. So given the region bounded by x equals 4y minus y squared and the y-axis, determine the volume of the solid generated by revolving that region about. Part A, we're going to revolve it around x equals -2. Part B, we're going to revolve it around x equals 4. Part C, we're going to revolve it around y equals -2. So let's remember that, first of all, some of us are uncomfortable working with the x equals style equations. You can literally flip every variable in this problem and get an equivalent expression. So you could call this y equals 4x minus x squared, but then you would also need to flip your rotational lines to be y equals -2, y equals 4, and x equals -2, respectively. So let's get an idea what this looks like using Desmos. This is the line x equals 4y minus y squared, and it's a leftwards opening parabola. And we want the region as defined by the y-axis and that curve. So between 0 and 4, let's check to make sure those are correct. If we put those on the Desmos, 0, 0, and 0, 4, yes, those are correct. We have a region in there between 0, 0, and 0, 4, and bounded by the curve. That's the region we're going to talk about. First thing we're going to do is we're going to rotate that region around x equals -2. So the first thing is, because we're rotating around x equals -2, we can think of it as being parallel to the y-axis. And thus we're going to do this process similar to how we would if we were rotating it around the y-axis. So I'm going to draw a brief sketch here. Let's call this part A. And we want x equals -2 right there. And our curve, oh, that's pretty bad, but we'll go with it. There. Now I'm going to take out the shading there actually. Now, in this particular situation, we're going to end up using the washer method because we're rotating around this line right here, the line x equals -2. We're going to call the big radius the distance from that line to the curve, and the little radius the distance from that line to the y-axis. Now, why do we do that? Because the region is bounded by the y-axis, so we do need to cut out that part. If we visualize the rotation there, we're going to have a hollow cylinder in the middle. So we're using the washer method. Another reason we could think about approaching this with the washer method is we're rotating around something that is like the y-axis, and our variables are in terms of y, so therefore we use the washer method. So the area formula on the washer method is pi big R squared minus pi little r squared. We already talked about big R is going to be defined by the big line right here and little r by the little line right there. So let's put it in terms of the variable we're working with. We're working with y, so I'm going to call this area with respect to y. So in this case, our big radius is rather complicated. 4y minus y squared represents the distance from the x-axis to the curve. That is not the whole distance of the large radius. So what we would need to do is add 2 onto that because the distance is actually 2 further. So our big radius is 4y minus y squared plus 2. And we're going to square that. Now our little radius is easy. Our little radius is this right here, and it is never changing. It's just the distance of 2. Remember though that it is squared. So applying the logic here that we've used in the past, the volume of the solid generated by this is the integral of pi big radius squared minus pi little radius squared. Let's bracket that off. And with respect to y. So let's discuss bounds. The bounds are still set by the lowest possible y value for our region and the highest possible y value for our region. Due to the fact that they intersect, as we talked about before, at the point 0, 0, and intersect again, remember we're talking about the intersection of the curve and the y-axis, at the point 0, 4, our y values go from 0 to 4. And we could do this by hand, but again, using the calculator, we will get that it is approximately 241.274 units cubed. All right, now we're going to move on to part B. Let me clear this. All right, so now we're rotating around the line x equals 4. So let's take a look what that would look like. So we're back to our graph here. The line x equals 4 is the green line over here. Notice that it intersects our parabola actually at the point 4, 2. And so we're just going to have to adjust our reasoning here. So let's go back and draw a picture of what we'd like. For part B here, what we have is we have our same curve, but we're rotating it around this line now. And so all we're going to adjust is our reasoning. Given that x equals 4 is similar to our y-axis and everything's in terms of y, we're going to use the washer method. So our area formula for the washer method is pi big R squared minus pi little r squared. But what is big R and little r in this case? So if I pick a point on our rotational axis, my big radius for my shaded region, remember everything inside of this right here is shaded. My big radius is going to be the distance all the way to the y-axis. And that's going to be the same no matter what point I pick. And that distance is always going to be 4. Now what is my little radius then? My little radius would be the distance from that point to the curve. Now this is a little bit trickier to reason out. So, switching colors here. The distance to the curve from that line can't be simply modeled with the equation. The equation gives us this distance right here in blue. So we have to use some geometric reasoning. And that reasoning is that if we have this whole section, which is 4, it's going to be equal to the short region plus the long region. The short region is what we want. That's our little r. But the blue region is the distance of the curve, 4y minus y squared. So we can solve for our little radius by simply subtracting it over. Our little radius is 4 minus 4y minus y squared. Now I'm going to simplify this just to make it easier for our calculus purposes. 4 minus 4y plus y squared. And so my little radius is 4 minus 4y squared. Oh, I'm sorry. I have an extra square in there. All right, now that I've fixed that, 4 minus 4y plus y squared, quantity squared. Now, we want to talk about the volume of this. Again, the volume will be the integral of that. Simplifying that 4 squared there. And dy, because we're working with respect to y. Our bounds are still from the bottom of the region to the top of the region, so our bounds are still 0 to 4. And again, using a calculator, we get that comes out to be about 160.850 units cubed if you wish. All right, let's do part C. All right, Part C is revolving around the line y equals -2. This is going to get a little tricky because we're rotating in a different direction now. Y equals -2 is a horizontal line. And so if we look at that horizontal line, we're going to run into a problem that the variables we're working in don't match our axis of rotation. And in that situation, we're going to switch to the shell method. So for part C, sketch what we're looking at here. We're rotating around the line y equals -2. Now, y equals -2 is similar to our x-axis. If we were rotating this curve around the x-axis, we would notice that our axis of rotation does not match the variables that we are working in. So you have two options. Switch the variables, and if that's not possible, switch to the shell method. So we're going to have to adjust the shell method here for this curve. So the area formula for the shell method is always 2 pi r h. H being the height of a cylinder of the object, and r being the radius from the axis of rotation. So if I visualize a cylinder here, I'm going to put it in a different color. Let's say that we have this as the long part. We're rotating it all the way down to here, will be the other side of it. It's going to have a long section here. And that's what our cylindrical shell will look like. So, given that cylindrical shell, working in our variable here, what is the radius? Well, the radius is the distance from the axis of rotation to the edge of the cylinder. Axis of rotation to the edge. So how do we represent that in this case? Well, first of all, the distance from the x-axis to the any point within the curve could be called y. And that would just be from the axis to there. The distance from the axis to the x-axis, the axis of rotation, is 2. So the radius of this is going to be y plus 2. What would the height be? Well, given that we're talking about this y, this is our height right here, and that's defined by the curve. So if our y is given there, our height would just be 4y minus y squared, defined by the curve. And again, same logic. If we want to take the volume of something like this, we want to take the integral of it. With respect to the variable we're working in. Bounds would still be 0 to 4, as we're still going from the point right here to the point right here, and that is the variable we're working in, is y. And so given that, we get an approximate volume of 268.083 units cubed. All right. Moving on to a new example, we're going to find the volume of the solid generated by rotating the region bounded by y equals x and y equals x to the 0.5 about the lines y equals 5 and x equals -1. So remember that y equals x to the 0.5 is really just the square root of x. So let's get a picture of what that looks like. I've graphed the two curves here, and we can see they intersect at the points 0, 0, and 1, 1. So that's the region bounded by those two curves, that thin sliver in between the red and blue there. So if we're going to rotate around the line y equals 5, I'm going to have to zoom out a little bit. Y equals 5 is way up there. So we're going to have this very thin sliver rotated at a very large distance. So the drawings I do are probably not going to be to scale. So for part A, if we sketch this, we'll get this region right here, rotate around the line y equals 5, and our equations are y equals x and y equals root x. Now, if we notice, the line y equals 5 is parallel to the x-axis, meaning that we can do it as a washer method because our variables are in terms of x and our axis of rotation is similar to the x-axis. So we're going to talk about big radius squared minus little radius squared. So the area formula when doing a washer is pi big R squared minus pi little r squared. In terms of x, our big radius, and this is where you have to get creative, is not, the big radius is at the line y equals x, but that's not the radius. Y equals x represents this distance right here. So what we're going to do for the big radius is we're going to take the entire distance. The entire distance here would be 5 from the axis of rotation down to the x-axis, and we're going to subtract off that x. Our big radius is 5 minus x. Similarly, our little radius is going to be 5 minus root x. Because the distance here is 5, we remove everything up to root x, and that'd be our little radius. So our volume, I'm going to use a different notation than what you're used to here, is the integral of our area function, just so I don't have to rewrite it a bunch. So we're just taking all of that, putting it right there. And the bounds would be the bounding of our region in terms of x. So the bounds are 0 to 1. And we said it's a very thin sliver, and we get a very small area for the amount of distance we're covering. We get an area of 4.712. All right, on to part B. Now we're going to be rotating around the line x equals negative 1. So if we draw our region, the line x equals negative 1, we realize we're rotating in the other direction now. So we have two options. We can go with the shell method, or we can adjust our equations. So instead of using the line, which is what I'm going to do, instead of using the line y equals x, I'm going to treat it as x equals y. And instead of the equation y equals x squared, or sorry, y equals the square root of x, if y equals the square root of x, then algebraically x equals y squared for what we're doing currently. And we can use the washer method because now our variables match a similar axis, the y-axis. So our area formula here is going to be the pi big R squared minus pi little r squared. We're going to put it in terms of y because that's the variable we're working in. The big radius would be the distance from here to the outside. So that is the line. So our big radius is 1 plus y squared. Or sorry, our big radius is just 1 plus y. 1 being the distance here, and y being the distance there. The short radius would be 1 again here, plus the distance to the curve. So that'd be 1 plus y squared. Our volume in terms of y, and I'm going to use that same notation again, is the integral of our area in terms of y, dy. Again, that means all this goes in there. And our bounds are now the y bounds. Luckily for us, these points that intersected were 0, 0, and 1, 1. So even if you mixed up your x and y bounds, you'd still get it right. But it's 0 to 1. And again, we'll get a small area because this is a very small region. 1.466. Alright, ladies and gentlemen, sorry about the long video, but this is a fairly complicated topic. I want to give you a lot of examples for it. And I assume it's going to be a point that we talk about when we have our session where we meet up and talk about these problems. So, I hope everything's going well for you. Let me know if you have any questions in the comments below.